Greetings! Today we will calculate the vertical displacement of point C. We will only consider the effect of bending moments. We will integrate using several different methods. Let's start with analytical integration to show that it can be done, although it is rarely used in practice. Especially since in this problem we can simplify the integrals considerably, and it doesn't really make sense to do it analytically. This is just to show that it is possible. Then we will move on to the Wereszczagin integration method. I will explain exactly how we will integrate the Wereszczagin method when we get to that point. For now, let's focus on drawing the moment diagram. First of all, there is no need to calculate the reactions here. We have an example where we only have a fixed support on the left side, and we can draw the moment diagram to the right practically straight away, without paying any attention to the reactions occurring at point A. Additionally, in this task, we will write out the bending moment function for the segments, so later we can conveniently use the analytical integral. So now we have two intervals of variability. The first variability interval is from C to B. Let's mark it, this is our x1, let's say, and then we will have x2 here. Of course, these are things we can quickly determine, in theory at least, from the course of material strength, or mechanics, depending on how it was conducted by whom. So now we have this x1 is within the interval from 0 to 2. Here, the bending moment is actually quite simple. The bending moment is -10. It's understood that these are K and M, and we will not complicate things further by writing it out at this moment. So we can already draw this is a constant value within this interval. We have -10. Next we have x2, which belongs to the interval. Now with the notation we've established, we need to record that this is from 2 to 6. And our bending moment, let's say it's mg2, that was mg1, it equals. Still -10, but -1/2 times 6x minus 2 squared. And we leave it in this form. We can slightly simplify it if we like. -10 minus 3, x minus 2 squared. Okay. At the boundary points, we will still have -10, however, let's calculate mg2 from 6. Let's quickly calculate using the calculator. It comes out to -58 kNm. Let's draw it. Of course, there will be a parabolic graph here. It doesn't make much difference, or maybe otherwise. There will not be any extreme value at any point in the interval for sure, because you can see at a glance that the shear forces will not intersect with the axis. But we are not particularly interested in that. In practice, it doesn't really matter to us whether there will be an intersection point for the shear forces and whether we will have an extremum, but it will go to the right. Kn times m. Okay, now we are moving on to the second part of the task, which is calculating the displacement at point C. If we calculate this displacement, we will need a completely clean system, to which we will transfer a unit force. So it's like we're drawing this beam a second time. Of course, at point A there is still a support, and now at point C there is some fictitious force of value 1. The graph here is trivially simple. It is visible to the naked eye, because here we have 1 times 2, which is -2, times 6, which is -6, small m. And by the way, this has a dimension of a meter. Let's write down this function. So m1 equals -1 times x, which is x, and m2 is also equal to x. Okay, now, we can already analytically calculate the displacement of point C, because yc is equal to 1 over ej, and formally we will write down an integral. Integral of mg mdx? mg times m, of course, over the entire length. In practice, since we have two variability intervals, then we integrate 1 over ej, open a bracket and integrate from 0 to 2. This is mg1 times mdx. Add. Integral from 2 to 6. m1, of course. mg2 times m2 dx equals. Of course, 1 over ei is written all the time. And inside we have an integral from 0 to 2. 10 times x. It was minus times minus, so it's a plus. Add an integral from 2 to 6 of 10 times x plus 3 x2 squared times x. Of course, we could split the second integral into two integrals, but at this point, it doesn't make sense, because we are calculating this on a calculator anyway. Whether you enter it into a calculator or calculate it manually as you prefer. However, when we have an integral of this type as here, it is much more beneficial to calculate it quickly on a calculator. We get 1 over ei times 500. We know that point C will move by 500 kNm2 divided by ei. Okay, we have calculated it in the analytical version. Now let's move on to how to do it simpler, faster, and more pleasantly. Without writing out the functions, mainly. Almost without writing out the functions. Because as you'll see in a moment, One of these functions will be needed in most of these methods that we'll be using, but not in all of them. It depends on what one prefers, so one can really integrate like that. And now the first version of this integral will be an integral where we will use a simplified formula, that is, this formula L6, etc., etc., etc. However, I'll show two versions now. A version with continuous loading, and without continuous loading, that is, with or without a parabolic graph. And now, what does it look like in practice? We are going to erase it because it's not needed for us. We memorize that it is 500 over EI to compare that, hey, it's okay. We don't need these things at all, and we won't need them anywhere as far as I recall. So only this remains. Unfortunately, we will need this because we have to calculate mg2 in the middle of interval BA, that is, for 4. Well, for 4, we plug it into the calculator. We get a value, let me recalculate it, minus 10 minus 3 times 4, 2 squared. We get minus 22, okay. We will use this in a moment. But for now, we have this. Let's write out how this integral looks in general. 1 over EI. The definition would of course be the same, so we skip the definition. However, we are integrating two intervals, so we write down both of these intervals. Here we have our parabolic shape. If you make ugly drawings like I do, you can write that this is a second-degree parabola. Value 58, value 10, 4 meters. And below we have a trapezoid with values 2 and 6. Okay, we add the second interval. The second interval is simple because it's minus 10 and 2. And now, if we wanted to strictly use this formula for L6, we have such a situation. For the integration of a trapezoid with a parabola, a trapezoid that contains a parabola with a trapezoid, we have a formula that looks like this. I take L6, which is 4/6, and now I take one of the values of the trapezoid, on the left side for example, which is 6, times the value on the same side, which is 58. Add twice the value in the middle. The whole thing is positive. We have times, so there's really nothing to ponder about. All the values I would be using would be negative if I wrote it down formally. Here I would have minus 6 times minus 58, so it's clear that the whole will be positive. Add the other side, which is 2 times 10 in parentheses, add 2 times 22. Again, this formula is trivially simple, and we add using the formula for L6 as well. But for a trapezoid with a trapezoid, we have 2/6. I have drawn 2 meters here, 2/6, and we remember this formula. 2 times what's on the same side, which is 2 times 10 squared. Add 2 times what's on the same side, but it cancels out here. Add what's on the opposite side, so it cancels out here, but here we have 10 times 2. Of course, as usual, I forgot 1 over I, so we add 1 over EI. And we quickly compute it with a calculator. I calculated it earlier, it actually comes out to 500. But just for formality, I'll quickly input it into the calculator again to make sure that I didn't accidentally make any mistakes when rewriting it at this point, essentially when writing it down. But it seems to be okay. So the result came out exactly the same as with the analytical method. We didn't have to write out the equal parts for intervals, and above all, it turned out, in my opinion, much simpler and faster. However, this is a version, let me say, currently preferred by me personally. Now, I'll show you a version that I integrated once before because it's even better in terms of how many equations of internal forces we have to write, because we don't really have to write any. So, we completely discard internal force equations in intervals. We keep only what we have already drawn, which is keeping our graphs. We would be able to draw graphs without writing out the internal forces for individual intervals depending on x, merely by listing values at points. And now we'll break apart this first figure into a trapezoid and a parabola. Now, we always have the right, when it's a parabola, to exclude it from other figures in this way, leaving us with a trapezoid 10, 58 here, and a trapezoid 2, 6 here, which is generally something we can integrate, right? A trapezoid with a trapezoid 0, 6 further, 4 meters. Here, delicate magic happens because you simply need to take it on faith for now, that by using the proposals, we can prove that we eliminate the parabola, and here in the middle we have QL2, 8. We will now calculate QL2, 8, so that later it can be easily substituted. Q is 6, L is 4 squared, and divided by 8 gives us 12. And here, we still have our unfortunate trapezoid 2, 6, which means nothing changes in this interval. Now it changes in terms of external load. Add the end part without changes. 10, 2 meters, 2. And now we know how to integrate a trapezoid with a trapezoid. So we integrate 1ej, 4, 6, 2 times what's on the same side. That is 2x58, x6 plus 2x10, x2 plus 10x6 and plus 58x2, which is each time on opposite sides. Add. Again, we use the formula directly from the tables. Alternatively, one could also use the definitive formula here. It doesn't really matter that much, in fact. What matters is that we eliminated the parabola, so we either use the formula from the tables or the definitive formula, which is essentially optional, but now let's use the definition here. But let's remember one important thing. Here we won't have a plus, but we will have a minus. Now why is that? Because this parabola is positive. This parabola is positive, firstly, because when we look at the drawing, we see that this parabola, I stress this is a mnemonic method, not consistent with how it's actually supposed to be discussed. However, we can imagine that this parabola sort of reduces the trapezoid. It creates a concavity in the trapezoid. However, more formally, we know the formula, the plot for this simplest loaded beam, with continuous loading. We know that the bending moment here is under the axis, thus it is positive. You can either memorize it this way or that way. It doesn't matter. Now, let's say we're calculating from the definition. So we have 2/3 times 12 times 4, which is obviously the area of the parabola. And now, the center of gravity of the parabola is exactly in the middle of the interval, meaning for 2 meters. And for these 2 meters, we need to calculate the value for the trapezoid. This is very simple because we see that this trapezoid increases from 2 to 6 over 4 meters. Thus, really, every meter the value increases, the plot by 1, so in the middle it will be a 4, meaning times 4, and we continue. The last figure is also integrated directly from the definition. It is already positive, and we get 1/2 times 2 times 2 times 10. So we actually took the area of the triangle, which is the area of the lower figure. Here we took the area of the upper figure. Notice that it doesn't matter. We can take the area of either the upper or lower and the height at the center of mass of the other. It doesn't matter if it's the lower or upper. We integrate the same way. Now, what I calculated earlier was correct, and it actually comes out to 500. So that's great. We have another version. Let's emphasize that the previous one is really preferred. This one is more for when we don't want to write down the equation for the bending moment in a given interval. It also depends on the specific task. In this case, there's no big difference which method we use because the equations are very simple. It will be more interesting with frameworks, but for now it's quite indifferent. Now, I will show a version in which we integrate it directly and only from the definition. That is, we will integrate from start to end using only the definition. What will actually change? Our first section will change, right? Because in the first section, maybe that's too much to say the first section. This trapezoid 5810 changed for us. Obviously, we could integrate a trapezoid with another trapezoid from the definition. No one will stop us, but we would have to find the center of mass of the trapezoid. Generally, finding the center of mass of a trapezoid is entertainment for long winter evenings. We definitely won't deal with it here because it's a waste of time. And mainly in practice, it's not really used. It would unnecessarily complicate things. So this part will change, right? And we'll check if the result is good. Instead of this trapezoid, we will make 2 triangles. So we will split the trapezoid into 2 triangles. Syntax with the superposition method. We have a sacred right to this. So now, we have trapezoid 58. Also 4 meters, of course. Sorry, obviously not trapezoid 58, but triangle 58. And trapezoid 6x2. Here, on the other hand, we have a triangle with a height of 10. And here we obviously have a plus. So the difference is that instead of using sixths, we use the definition. The definition says, the area of any figure. So let's take the area of the triangle. 1/2 times 58 times 4. And now, the centroid of this triangle is here. This is a distance of 2/3 of 4 meters. So, projecting downward, we must calculate the height of the trapezoid at this point. But really, we see that it's a trapezoid, which, as we already discussed, increases by 1 per meter. So when we have an increase of 1 starting from 2, it grows by 8/3. Here we have a funny value of 14/3. So times 14/3. Add. Here we again have 1/2 times 10 times 4. The area of our triangle. And again we project. But here, notice that we have 1/3 of 4. And I'm going from the right side because it's easier to calculate the height of the trapezoid. Project? And we have it analogously as before, but we have 4/3, not 8.3. So here it is, 10/3 times 10/3. The rest remains unchanged. Let's quickly calculate to see if it matches. 1/2 times 58 times 4 times 14/3. Add 1/2 times 10 times 4 times 10/3. Subtract 2/3 times 12 times 4 times 4. Add 1/2 times 2 times 10. And ends up with 500. I mean, regardless of which way we reach this result, it must come out the same. However, it's nice to be aware that we can perform these calculations in many different ways. Although the truth is that if you memorize and learn to use the formula for L6, in 9 cases out of 10, it is the best. The simplest to use, except that you need to record the graph. Equation of internal forces, not just the graph itself. We will discuss this more broadly when it comes to frames. However, here, as I said, the simplest is L6. However, if we weren't integrating, we would obviously get the exact same result. As for this topic, that's everything. Thanks a lot. Best regards.